Good morning. My name is Ian Krouse. I'm from Georgia Gwinnett College. Today I'll be telling you about an Excel activity that I do with my non-science majors, where we calculate the mass defect and the binding energy per nucleon, and we make a plot. Just a quick blurb about my institution. I am from Georgia Gwinnett College, opened up in 2006, and open access. The course that this activity is in is Physical Science 1101K. It does have a lab component, and we can change our themes. And in my theme, I use primarily dry Excel activities. In this activity, students use Excel to calculate the mass defect for a given nucleus and then convert it into the binding energy per nucleon. This is the scary looking formula for mass defect, but for my students I break it down into 4 pretty easy steps. The first is finding the calculated or theoretical mass of a given nucleus. Then we subtract the actual mass, and that little bit of difference in the mass is called the mass defect. That has been converted into nuclear binding energy, which we can then convert into mega electron volts, and then we just find it as a ratio of nuclei. On the next slide, you're going to see an Excel demonstration showing what the students actually do during the lab period. Right. So this is the Excel interface. This is what the students are given. You can see there's a variety of data for about 150 different nuclei. And what the student needs to do is essentially start putting in formulae to mirror what they need to figure out. And one of the big mistakes students make, they try to put the actual numbers in instead of using formulae, and so that's something that you really want to head off early if possible. Now in this cell, this is where we're actually going to put the number of protons times the mass of proton plus the number of neutrons times the mass of a neutron, and that gives us our calculated mass. And then we have the actual mass, which is here, and this also causes a little bit of trouble because students aren't quite sure why we have these superfluous columns, but you'll see why in a minute. So if you remember, there's 4 steps. We just did the addition step. The next step is going to be a subtraction step, and so we're going to subtract the actual mass from the theoretical mass. And then the third step is multiplying. So we're going to take this cell here and multiply it by the energy factor to convert AMU into mega electron volts. And then lastly, we take that energy and divide it by the mass number. And so this is why I have these extra columns, is because a lot of that information has shifted to the left. And if the student manages to fight through this, they should be able to just autofill. And prior to even touching Excel, I've told them to do a couple of examples on pen and paper, and that way they can come down. So for example, they're supposed to do sodium 23, and they should already have done that, and they can come and they can double check and see, oh, my math is working out with what I calculated. Once they do that, then they can make the plot, and we're going to show that on the next slide. The deliverable for this lab activity is a plot that looks something along these lines. To close out this quick distillation, please let me know if you have any questions or you want more one-on-one assistance. I'm more than happy to share the slides, share the Excels, what have you. The students do see this concept again. They see it on quizzes and exams, and they tend to do fairly well. We also revisit the concept later on when we get to nuclear chemistry, and it is hoped that this activity will also be adapted for use in our online courses such as general chemistry, both synchronous and asynchronous. Thank you.